All right, welcome everyone to another deep dive. Today we're going on a little journey. We're diving into the world of 2D materials.
2D materials.
They're these incredibly thin materials, like just a few atoms thick.
Right.
And they're causing like a huge buzz in science and technology.
Yeah.
So we're going to try to unpack what makes them so revolutionary.
Okay.
And we're going to be looking at an essay by Jörg O. Schneeppet called, and I'm going to butcher this, 2D Materialien. Revolutionäre Werkstoffe wie Graphene.
Right.
Our goal today is to help you really get a grasp on like the core concepts and the potential of these materials, you know, without getting too bogged down in all the technical jargon.
Yeah.
So like think of it as your shortcut to understanding why everyone's so excited about these 2D materials.
Exactly. And at their most basic level, you can think about them as materials defined by their thinness, sometimes just a single layer of atoms.
It's hard to even picture something that thin.
It is. It's like a sheet of something so thin that at the atomic level, it's practically flat.
Yeah, so what would be some like real world examples of these atomic sheets?
So the most well-known one is graphene.
Okay.
And that's a single layer of carbon atoms. But there's a lot, beyond that. There's things like transition metal, dichalcogenides,
Okay.
TMDs,
TMDs, right.
or hexagonal boron nitride.
Right.
Each one has a different kind of arrangement of atoms.
Okay.
But they all share this incredible thinness.
So why are scientists so captivated by these super thin materials? What's the big deal?
Well, there's a few things. One of the big things is their high specific surface area. So if you think about it,
Okay.
a material that's almost all surface means there's a lot of area for interactions to take place.
Yeah.
And that's really useful for things like catalysis and sensing.
Wow.
And then, on top of that, they have electrical, mechanical, and optical properties that can be really different from their thicker counterparts.
Okay.
So it's kind of like a whole new world of materials to explore.
So the essay talks about, the discovery of graphene as being kind of this big turning point. Like, how did this whole field even get started?
So it really kicked off in 2004.
Okay.
When Andrei Geim and Konstantin Novoselov, they isolated graphene.
And they did it with like regular sticky tape, right?
Yeah, they used this technique called mechanical exfoliation.
Okay.
That, it's also known as the Scotch tape method.
Yeah.
Basically what they did is they took some graphite.
Okay.
Like the stuff in a pencil. And they just used tape to peel off layers. And they kept doing it.
Wow.
Until they got down to, single atom, thick flakes of graphene.
So this seemingly simple act, like, revealed all these kind of crazy characteristics.
It did.
What made graphene so special?
So they found that it was a really good conductor of electricity.
Okay.
It was incredibly strong, like way stronger than steel.
Wow.
And then on top of that, it was transparent.
Yeah.
So you had this kind of combination of properties that nobody had ever seen before.
And it wasn't just about, graphene itself.
Right.
It kind of opened up the possibility of this whole new class of materials, right?
Exactly. Like by showing that you could actually create and study these single atom thick materials. Yeah. It basically created this whole new area of research.
And they even got a Nobel Prize for it.
They did.
So that must mean it was pretty important.
In 2010, they were awarded the Nobel Prize in Physics.
Wow.
So yeah, it was a pretty big deal.
So these 2D materials, they're not just stuck in research labs, are they?
No, definitely not.
The essay talks about, how important they are for research, but also, how they're being used in industry.
Right, exactly. They have lots of potential uses in all kinds of modern technologies.
Yeah, like what are some specific areas where we might see these materials, having a real impact, like soon?
So in electronics, for example, they can make faster and more efficient transistors.
Okay.
And that means, faster computers and smartphones and things like that. And because some of these materials are flexible, you can even make flexible displays.
That's cool.
Like imagine a phone that you can roll up.
Yeah.
Then there's energy storage.
Okay.
They're looking at them for improving batteries and supercapacitors.
Okay.
So that could mean, electric cars with longer ranges.
Yeah.
Or devices that charge in just a few seconds. And then there's also, biomedicine.
Okay.
So they could be used for, new diagnostic tools.
Okay.
Or even targeted drug delivery systems.
So, I know the essay mentioned something about how people are trying to incorporate these materials into existing industries.
Yeah.
Like the semiconductor industry.
Exactly.
Can you talk about that a little?
So the semiconductor industry is always trying to make smaller, faster, more efficient devices.
Right.
And these 2D materials, because they're so thin and conductive,
Yeah.
they have the potential to, replace or enhance traditional materials like silicon.
That's interesting.
And they could really, push electronics to a whole new level.
So it's not just, improving existing tech. It's also about quantum research, right? What can these materials tell us about, the quantum world?
So 2D materials, they have this unique set of properties.
Okay.
That makes them really good platforms for exploring quantum mechanics.
Mm-hmm.
So you have things like graphene.
Yeah.
They exhibit really interesting phenomena like, the quantum Hall effect.
Okay.
And really unusual electronic band structures.
And that's important for understanding the quantum world.
It is. Like studying these phenomena at the nanoscale,
Mm-hmm.
that helps us understand, the fundamental laws of physics that govern the quantum world.
So these materials aren't just cool. They're like helping us understand the universe better. I think the essay even hinted that some of these materials might be, important for building quantum computers, right?
Right. So certain 2D materials, they have these properties like long spin coherence times.
Okay.
And they even exhibit superconductivity.
Okay.
And those are really important for building quantum computers. So like if we can figure out how to really precisely control the quantum states within these materials,
Mm-hmm.
it could be a huge step towards actually making quantum computers a reality.
Okay, so now that we know, what 2D materials are and why they're so important, let's dive into some of the detail, right? The essay gives a more detailed definition of 2D materials and explores, some of their unique physical and chemical properties.
Yeah.
So let's start with, some of the structural features of these materials.
So as we mentioned, the big thing about them is their monoatomic thickness.
Mm-hmm. Mm-hmm.
That's what really sets them apart.
Yeah.
They're just a single layer of atoms. And within that layer, you have this really regular pattern of atoms called a crystalline lattice.
Okay.
And that ordered arrangement is really important for a lot of their unique properties.
So this regular arrangement of atoms, this periodicity you called it,
Right.
that's directly related to their properties.
Yeah, basically the way that the atoms are connected and how they're arranged in space, that determines how electrons can move through the material.
Okay.
And that affects things like electrical and thermal conductivity and even their optical properties.
So can you give us an example? Like how does that work in something like graphene?
Sure. So in graphene, you have these carbon atoms.
Okay.
And they're arranged in this honeycomb structure
Mm-hmm.
with a very specific bond length,
Okay.
about 0.142 nanometers.
Right.
And that 2D geometry, that restricts how electrons can move.
Okay.
And that leads to some, interesting quantum mechanical effects.
So are we talking like perfectly arranged atoms here?
Not always.
The essay mentions, crystalline order and defects.
Right. So in a perfect world, you'd have these perfect crystal structures.
Right.
But in reality, materials always have imperfections,
Okay.
which we call defects. And these defects can be like, missing atoms or atoms that are replaced by different types of atoms or, dislocations in the lattice, places where the regular pattern is disrupted.
And are these defects always a bad thing? Do they always make the material worse?
It depends. Sometimes they can be bad, like, they can scatter electrons.
Okay.
And that reduces electrical conductivity.
Mm-hmm.
But in other cases, they can actually be good.
Really?
Yeah. Like, for example,
Okay.
certain types of defects in graphene,
Mm-hmm.
they can actually increase the material's chemical reactivity,
Okay.
which can be helpful for things like catalysis.
Yeah.
So it's really about understanding and controlling the types of defects
Okay.
to get the properties you want.
So defects, not always the enemy. Let's move on to like some of the unique properties of 2D materials, right?
Right.
The essay talks about, these amazing electronic properties and mentions, the Dirac cone in graphene. What's that all about?
So graphene has really interesting electronic properties.
Okay.
And that's mainly because of how its electrons behave.
Okay.
So in a lot of materials, electrons have mass.
Right.
And their energy, it changes with their momentum in a kind of predictable way.
Mm-hmm.
But in graphene, the electrons, they act like they have no mass.
Okay.
They're what we call quasi-massless Dirac fermions.
Quasi-massless.
Yeah, it's a mouthful.
Yeah.
But basically it means they follow the same equations as massless particles, like photons.
Okay.
And because of that, their energy changes linearly with their momentum.
Mm-hmm.
And we visualize that relationship with something called a Dirac cone.
Okay.
And because of this weird behavior, the electrons can move through the graphene lattice with almost no resistance. So you get this really high electrical conductivity.
So graphene's special because it's got these massless electrons, basically.
Yeah. You can think about it that way.
What about other 2D materials? Do they have this property too?
So not all 2D materials have the same electronic properties as graphene.
Okay.
So like graphene's a semi-metal, which means it has no energy gap between its conduction and valence bands.
Mm-hmm.
But a lot of other 2D materials, like, the TMDs we talked about before,
Yeah.
they're semiconductors.
Okay.
And they have what we call a direct band gap,
Okay.
which is a range of energies that electrons can't occupy.
Okay.
And that band gap is really important for optoelectronics.
How so?
Well, because it allows them to absorb and emit light at very specific wavelengths.
Interesting.
So, different structures lead to different electronic behavior, and that opens up a whole range of possibilities.
Right. The essay also mentions things like, thermal conductivity.
Yes.
And mechanical stability. And graphene seems to be, pretty awesome in those areas too, right?
Yeah. Graphene has a very high thermal conductivity.
Okay.
So it's very good at conducting heat.
Mm-hmm.
And that's because of the strong bonds between the carbon atoms.
Okay.
And the fact that there's minimal scattering of phonons.
Phonons.
Yeah, those are the vibrations that carry heat.
Okay.
So it's kind of like a superhighway for heat.
So what about its strength?
Oh, it's really strong.
I remember hearing that it's even stronger than steel.
Yeah, that's right.
How is that even possible?
So despite being so thin, graphene has really high tensile strength.
Okay.
Which means it can withstand a lot of force without breaking.
Mm-hmm.
And it's also very light and flexible.
It's like the best of both worlds.
Yeah, you can bend and stretch it without it breaking.
Yeah. So you can use it for all these, flexible electronics and things.
Exactly.
The last property the essay mentions is surface reactivity.
Yes.
And chemical functionalization.
Right.
Why are these aspects important?
So because 2D materials are basically all surface.
Okay.
They're very reactive.
Mm-hmm.
And that's useful for things like catalysis.
Okay.
Where reactions happen on the surface.
Right.
And sensing, where the material interacts with its environment.
Yeah.
And we can actually modify the properties of these materials.
Okay.
By attaching different chemical groups to their surfaces.
Mm.
And that's called chemical functionalization.
So it's, customizing the material to do what you want it to do.
Exactly.
You mentioned before, how graphene can be converted to graphene oxide.
Right.
How does that change its properties?
So when you oxidize graphene, it becomes soluble in water.
Okay.
And it gets these new chemical groups that make it, reactive in different ways.
Interesting.
And that opens up possibilities for things like drug delivery or creating new composite materials.
Okay, so we've talked about, what 2D materials are and some of their properties.
Right.
Let's go back to graphene for a minute, since the essay really focuses on that.
Sure.
We talked about its discovery, but, how do you actually make graphene?
So the original method was that mechanical exfoliation, the Scotch tape method.
Right.
And that's still used for research.
Okay.
To make really high quality samples.
Okay.
But it's not very practical for large scale production.
Right. You can't just be peeling tape forever.
Exactly. So for larger quantities, there's a method called chemical vapor deposition.
Okay.
Or CVD.
Easy D, all right.
And in that method, you basically have this carbon containing gas.
Okay.
Like methane. And you heat it up.
Oh, okay.
And it decomposes on a metal surface like copper or nickel.
Okay.
And that forms these, large sheets of graphene.
So that's how they make it on a larger scale?
Yeah, it's one way.
Okay.
There's also, a method where you chemically reduce graphene oxide.
Okay.
And that can be cost effective. But the quality of the graphene isn't always as good.
Interesting. Let's talk a bit more about graphene's properties, in detail, like its conductivity.
Okay.
You said it was, exceptionally good, but can you break it down a bit?
Yeah. So as we talked about before with the whole Dirac cone thing, the electrons in graphene, they move really easily.
Okay.
Because they don't experience much resistance.
Right.
So you get these high current densities,
Okay.
much higher than you would get in a normal metal. And it's important to note that the conductivity, it's not the same in every direction.
Okay.
It's what we call anisotropic.
Oh, right.
And then under certain conditions, like really low temperatures and high magnetic fields.
Okay.
You get this really cool thing called the quantum Hall effect.
The quantum Hall effect.
Where the conductivity becomes quantized.
Okay.
It can only take on specific values.
Interesting. And what about graphene's, mechanical strength and flexibility? You mentioned that it was, stronger than steel and super flexible.
Right. So that incredible strength comes from the strong bonds between the carbon atoms.
Okay.
And the flexibility comes from the fact that it's only one atom thick.
Right.
So it can bend and deform without those bonds breaking.
That's pretty cool.
And that combination of strength and flexibility.
Yeah.
It's really good for things like, flexible electronics and displays.
Yeah.
Yeah.
Yeah, that makes sense. And lastly, you said that graphene was also super transparent.
Yes.
How does that even work?
So even though it's really good at conducting electricity, it only absorbs about 2.3% of visible light.
Wow.
So most of the light just passes right through.
Okay.
And that's because the electrons are really mobile. So they can conduct electricity without absorbing too much light.
That's fascinating. So you're saying that it's transparent because the electrons are so good at moving around.
Yeah, you can think of it that way.
So what are some of the ways, this transparency could be useful?
So that combination of transparency and conductivity, it makes it really good for things like transparent electrodes.
Okay.
You could use it for solar cells, touch screens, transparent displays.
So imagine a phone that's completely see-through.
Exactly.
That's pretty wild. So now that we've, talked about graphene in detail, let's move on to some of the other 2D materials, right? The essay talks about this whole diversity of materials beyond graphene.
It does.
So let's dive into that.
Sure.
So one of the ones it mentioned is TMDs.
Right.
Can you give us, a little more detail about what TMDs are?
So TMDs, or transition metal dichalcogenides.
Right.
They have this general formula, MX2.
Okay.
Where M is a transition metal.
Okay.
Like molybdenum or tungsten. And X is a chalcogen, like sulfur, selenium, or tellurium. And they have this layered structure.
Okay.
Where you have a layer of the metal atoms sandwiched between two layers of the chalcogen atoms. And the bonds within the layers are strong.
Okay.
But the bonds between the layers are weaker.
Okay, so they're kind of like stacks of atomic sandwiches.
Yeah, you could think about it that way. And then, electronically, they have a wide range of behaviors.
Okay.
Some are metallic.
Okay.
But a lot of them are semiconductors. And they have this direct band gap.
Okay.
Which means that they can absorb and emit light efficiently.
Okay.
So they're really good for optoelectronics.
Can you give us an example? What's a specific TMD and how would you use it?
So one example is molybdenum disulfide.
Okay.
Or MOS2.
MOS2, right.
And that has a direct band gap of about 1.8 electron volts.
Okay.
So it can absorb and emit light in the visible range.
Okay.
And that makes it good for things like, photodetectors, solar cells, LEDs.
Yeah.
And EMDs are also interesting for catalysis.
Okay.
Because they have this large surface area.
Right.
And you can introduce defects into them that can make them more reactive.
Okay.
So they could be used for things like, water splitting to produce hydrogen.
So TMDs, they're kind of like a toolbox of materials, right?
Exactly.
There's different properties, different applications. What's the next material that the essay talks about?
So the next one is hexagonal boron nitride.
Okay.
Or HBN.
HBN.
And that one's sometimes called white graphene.
White graphene.
Yeah, because it has a similar structure to graphene.
Okay.
But it's made of boron and nitrogen instead of carbon.
Right.
And it has very different properties.
Okay.
So unlike graphene, which is a really good conductor,
right,
HBN is a really good insulator.
So it does the opposite.
Yeah, basically.
That's cool.
It has a large band gap.
Okay.
So it doesn't conduct electricity very well. And it's also chemically stable. And it has a pretty high thermal conductivity.
So what would you use, an insulator like that for?
So you can use it as a substrate for graphene.
Okay.
Or other 2D materials.
Right.
Because you want to isolate them. You can also use it as an insulator in electronic devices.
Okay.
To prevent leakage. And you can even use it as a protective layer.
So even though it's an insulator, it's still pretty useful.
Yeah, it has a lot of important applications.
Okay, the essay also mentioned black phosphorus.
Right.
What's special about that one?
So black phosphorus In its 2D form, it's called phosphorine.
Phosphorine.
And it has a different crystal structure than graphene or HBN.
Okay.
It's called orthorhombic.
Orthorhombic, all right.
And that gives it anisotropic properties.
Meaning?
It means that its properties depend on the direction.
Okay.
So like its conductivity or its optical properties,
yeah,
they'll be different depending on which way you measure them.
That's pretty weird.
It is. It also has a band gap that you can tune.
Okay.
So you can change the band gap by changing the number of layers.
Interesting.
And that makes it promising for electronics and optoelectronics.
Okay.
But there's a challenge with black phosphorus.
What's that?
It's not very stable.
Oh.
It oxidizes really easily in air.
So it's kind of hard to work with.
Yeah. You have to be careful with it.
Okay, the last group of materials that the essay mentions is MXenes.
Right.
What are those?
So MXenes, they're a relatively new family of 2D materials.
Okay.
And they're made by etching out layers from these materials called MX phases.
The MX phase.
Yeah.
Okay.
And they have some interesting properties.
Like what?
So they can have metallic conductivity.
Okay.
But they're also hydrophilic, which means they like water.
That's a weird combination.
It is. But it makes them useful for things like energy storage.
Okay.
Water purification, sensing.
Can you modify them like we talked about with functionalization?
Yeah, you can functionalize MXenes by adding different chemical groups to their surfaces.
Okay.
And that lets you fine-tune their properties.
Cool.
And people are even making hybrid structures.
Okay.
By combining MXenes with other 2D materials.
Yeah.
Like graphene or TMDs.
So it's like, taking the best of both worlds.
Exactly.
So we've talked about all these amazing materials and all this potential.
Right.
But the essay does mention, that there are still some challenges, right?
Yeah, absolutely.
Like, what are some of the things that are holding back the widespread use of 2D materials?
So some of these materials, they're not very stable.
Okay.
Like, black phosphorus we talked about.
Right.
It degrades in air.
Yeah.
And then there's the challenge of producing these materials on a large scale and making sure that the quality is consistent.
Right, because if you're going to use them in real-world applications, you need a lot of it, and it needs to be good.
Exactly. And then there's the challenge of actually integrating these materials into existing technologies.
Right, because they're so tiny.
Yeah, it's not always easy to work with things at the nanoscale.
Yeah, I can imagine. But it sounds like, there's a lot of research being done to overcome these challenges.
Oh, definitely. This is a really active area of research.
So this has been a really, really fascinating dive into the world of 2D materials.
It has.
Thanks to, this awesome essay by Jorgo Schneeppert.
Yes.
So to kind of wrap things up, can you give us a quick summary of what we've learned?
Sure. So we've learned that 2D materials, like, starting with graphene, they represent this whole new class of materials.
Right.
With incredible properties that come from their thinness.
Yeah.
And they have the potential to change all sorts of fields. Like, electronics, energy storage, even quantum computing and biomedicine.
Yeah, the possibilities seem, pretty endless.
They do. And we've talked about all sorts of different 2D materials.
Right.
Graphene, TMDs, HHBN, black phosphorus, MXenes.
Yet they all have, their own unique properties.
Exactly. And there are still challenges to overcome.
Right.
Like stability, production, integration. But there's a lot of research happening to address these challenges.
So, to our listeners out there.
Yeah.
Given all this amazing progress with, 2D materials, what do you think is going to be, the most impacted, like, in the next 10 years?
That's a good question.
Like, what everyday technology is going to